Today we're going to look at the concept of calorimetry. Calorimetry is the measurement of heat transfer, and it's an experimental technique where we can see how heat transfers from one place to another, but we set up the experiment very carefully so that we know exactly where the heat is starting and where the heat is going. There's two different types of calorimetry. One type is called bomb calorimetry, and I'm not going to talk about that specifically right here. What I am going to talk about right here is what's called a constant pressure calorimetry. And in constant pressure calorimetry, the calorimeter, the device that we use in calorimetry, is open to the environment, and therefore it has constant pressure. So the way constant pressure calorimetry works is we use a insulated container, and often the constant pressure calorimetry is called coffee cup calorimetry because in a beginning lab class, coffee cups are often used. But it's an insulated container, and the insulated container is covered so that it's insulated on top also. And inside the container is placed some water. And remember, we know some information about water. We know that the specific heat of water is 4.184 joules per gram degree Celsius. In other words, if we heat up water, it's going to take 1 joule of energy to heat up 1 gram of water 1 degree Celsius. And I just said 1 joule, but not 1 joule. 4.184 joules of energy to heat up 1 gram of water 1 degree Celsius. And that's what the specific heat is telling us. For every gram of water, it's going to take us 4.184 joules of energy to heat it up. So if we put into this water a piece of metal, and this piece of metal is very, very hot, so it's a hot piece of metal, then that hot piece of metal is going to transfer heat to the water. And the metal is going to cool down, and the water is going to heat up. The metal is going to lose heat, Q amount of heat, and so Q metal. The water is going to gain heat, and since the metal is losing heat, we call it negative. The water is going to gain heat, which we're going to call QW, and since it's gaining heat, it's positive. And it turns out that the amount of heat the metal loses and the amount of heat that the water gains is equal to each other, but opposite in magnitude. So the negative of the Q of metal equals the positive of Q water. They're equal to one another, and this is the law of conservation of energy, or the first law of thermodynamics, that tells us that these heat values must be the same. The heat lost by one thing has to be the heat gained by another thing. And so in calorimetry, if we know how much heat the water gains, then we also know how much heat the metal lost. And what's nice about calorimetry is since we're using water and we know how much heat it takes to heat water up, we can find out the heat gained by the water very, very easily by using heat of water equals the mass of the water times specific heat of water times the change in temperature of water. And these are very easily measurable. The mass of the water is very easy to measure. Change in temperature of the water, very easy to measure. And then C is a constant that we already know. So we can find out how much heat the water gained by measuring the mass, plugging in the specific heat of water, and measuring the change in temperature of the water. And then once we know the heat lost by the water, we know the heat gained by the water, we know the heat lost by the metal, which was a much harder thing to measure. And so what we're going to do is we're going to do a practice problem using this concept of calorimetry where a piece of metal loses heat and some water gains heat. So here's a problem where we put a piece of metal into some water in a calorimeter. Let's see what we have. It says a 15.0 gram piece of metal that is 95.8 degrees Celsius, and I left off the degrees here. Degrees Celsius is placed in a calorimeter containing 245 grams of water that is 15.3 degrees Celsius. The metal and water reach a final temperature of 19.1 degrees Celsius. What is the specific heat of the metal? So we're going to write down our givens, and let's keep our information in two separate columns, one for water and one for the metal, and that way hopefully we can keep things straight. So for the water, well, let's just go through. We have 15 grams of metal. So we know the mass of the metal is 15.0 grams. If I keep going, it says that it's 95.8 degrees Celsius. So our initial temperature, because the temperature is changing here, our initial temperature is 95.8 degrees Celsius. So if we keep going, it's placed in a calorimeter that contains 245 grams of water. So the mass of the water is 245 grams. And the initial temperature of the water is 15.3 degrees Celsius. The metal and the water reach a final temperature of 19.1 degrees Celsius. So for both of these, the temperature final of the water is 19.1 degrees Celsius, and the final temperature of the metal is 19.1 degrees Celsius. So now we've got some information about the water and some information about the mass. Another piece of information that's not stated in this problem, but we do know about water, is that the specific heat of water is 4.184 joules per gram degree Celsius. It's kind of like back in gas laws when we talked about the ideal gas law and you knew R. You didn't have to be given R, you knew what R was. Same thing with the specific heat of water. We know the specific heat of water, and so that's a piece of information that we can use. So as we're going to solve this problem, we need to remember that to solve for the specific heat of the metal, which is what we're solving for, we need to remember that the Q for water, the water gains energy, and that's going to be equal to the negative of Q of the metal. In other words, whatever energy the water gains is the negative of the energy that the mass loses. And so we can plug into the equations for these two things. The Q of the water equals the mass of the water times the C of the water, specific heat of the water, times the change in temperature of the water. That's the equation for Q water. For the metal, same thing, except we have a negative sign in front. The mass of the metal times the specific heat of the metal times the change in temperature of the metal. And so now we're going to substitute into this equation all these values that we know. We know the mass of the water is 245 grams. We know the specific heat of the water is 4.184 joules per gram degree Celsius. And we know the change in temperature of the water is our final temperature minus our initial temperature. So final minus initial, 19.1 minus 15.3, and that is 3.8. So 3.8 degrees Celsius. So now we've got our information plugged in, substituted in for the water. For our metal, put the negative sign in front. The mass of our metal is 15.0 grams. The C is what we're solving for. And the change in temperature is our final temperature minus our initial temperature. So 19.1 minus 95.8, which is negative 76.7. So negative 76.7. And you'll notice that we have a negative temperature change because its temperature went down. And that's why we needed the negative out here in front, because a negative times a negative will give us a positive. And this side obviously is all positive. So that works the sign out by putting the negative in front. So now all we have to do is solve for C here. And to do that, we simply are going to simplify the left hand and the right hand side of the equation. So we're going to multiply all these values together in order to get them simplified. And when you do that, you get 3,895.304, and we'll worry about significant digits at the end. And if you'll notice, grams and grams cancel, degrees Celsius cancels with degrees Celsius, and we're left with joules on the left-hand side. Now we're going to simplify the right-hand side. So we're going to do 15 times negative 76.7 times a negative 1. So when we do that, positive 1150.5. So positive 1150.5. And over on this side, oops, I forgot my unit here. Over on this side, we have grams degrees Celsius. So that's our unit, grams times degrees Celsius. And then C is still there. We didn't get rid of C. So we have to make sure we keep C there. So now we need to get C by itself. We need to isolate our variable, which means we're going to divide both sides by 1150.5 to get C by itself. So we're going to divide this side by 1150.5, and we're going to divide this side by 1150.5. And when you do that, let me go ahead and show that. 1150.5 and divided by 1150.5, and that's grams degrees Celsius, and that's grams degrees Celsius. So notice that the 1150.5 divided by 1150.5 cancels, and we get our final value of C, which is 3.3857, etc., etc. And our unit is joules divided by grams degrees Celsius. So joules per gram degrees Celsius, which is the correct unit for specific heat. Now, significant digit-wise, if we look back at all the numbers we were given in the problem, our least number of significant digits was 3. So our final answer should be rounded to 3 significant figures, which makes 3.39 joules per gram degrees Celsius. And so this is the usefulness of calorimetry, the idea that we can set up an experiment where heat transfers from something we don't know much about to something we do know a lot about. And it allows us to solve for information about that thing we don't know. In this case, specific heat. And so that's calorimetry. Please look at the notes, the PowerPoint notes, because there's another practice problem in there, and you'll be able to work through that problem also. And we'll be doing this lab in class so that you can see how this works experimentally. So until then, goodbye.